Hi, my name is Neda and I'm going to tell you about buffer sizing in routers. High-speed routers in the backbone of the internet use very large buffers to store packets at times of congestion, which happens when packets cannot be sent out of a port as fast as they arrive. Today, a router's line card with a 10 gigabit per second interface is likely to have a buffer size of 1 million packets. This is based on a commonly applied rule of thumb, which requires a buffer size of RTT times C. RTT is the average two-way delay between traffic senders and receivers, and C is the output link bandwidth. While it may sound like a good idea to make buffers larger and larger to avoid any packet drops, a larger buffer is in fact not always a better choice, because of more queuing delay, complexity, cost, and power consumption. The buffer sizing rule of thumb is based on the dynamics of TCP. More than 90% of the internet traffic is TCP traffic, which has a closed-loop congestion control mechanism. TCP controls the transmission rate by adjusting the so-called window size. In its simple model, the window size is increased by a small amount when the sender receives an acknowledgement packet, and it's reduced by half when there is a packet drop. This forms the TCP sawtooth. The size of this sawtooth is equal to the buffer size provided by the rule of thumb to ensure that the buffer never goes empty and the output link always remains at full utilization, even when the transmission rate is reduced. The rule of thumb can be applied when there are a few TCP flows on a link, but with more and more flows, the size of the aggregate TCP sawtooth becomes smaller and the required buffer size reduces. Recent studies suggest that if the number of flows on the link is large enough, the buffer size can be scaled down by a factor of the square root of the number of flows without compromising the throughput. With 10,000 flows, the buffer size can be reduced 100 times, down to 10,000 packets in our example. But the buffer size could be reduced much further in fast backbone networks that interconnect many slow-access networks. Here, traffic becomes even smoother as packets of individual flows are spaced out when they are multiplexed onto fast backbone links. Our analysis shows that in this case, we can achieve high utilization with a tiny buffer size that is independent of the link bandwidth and delay, and is about 20 to 50 packets. Simulations and lab experiments validate these results and show that the throughput rapidly increases to 90% as the buffer size goes up from 0 to about 20 to 50 packets. Then the throughput continues to increase slowly and reaches 100% when the buffer size is RTT times C over the square root of n. Now let's try a real buffer sizing experiment in a network built over the Internet 2's backbone network. At the core of this network, we've deployed a number of NetFPGA routers. NetFPGA is a programmable hardware platform. The board has 4 GIGI interfaces, and because the entire data path is implemented in hardware, it can support back-to-back packets at full line rate. The size of the output buffers in NetFPGA can be changed as accurately as 1 byte at a time. These output buffers are monitored by an event capturing module on the board, which records all packet arrival, removal, and drop events. This allows a precise measurement of queue occupancy and throughput. In this demo, TCP traffic is generated by end hosts at Stanford and Rice University and goes through a bottleneck link running at 100 megabit per second between Los Angeles and Houston. We do our measurements on this link, which is color-coded here to show different amounts of link utilization. Using a control panel, we can remotely and in real time change the buffer size of the Los Angeles router and set it to any desired value. We can also change the number of TCP flows on the bottleneck link. Flows can be added or removed as desired. With more flows on the link, fluctuations in the link utilization become smaller and smoother, and the average link utilization increases. Now let's see what buffer size is needed for this bottleneck link. What the rule of thumb suggests here is 650 kilobytes or about 650 packets, shown by the red line. And if we divide this number by the square root of the number of flows on the link, we'll have the black line. Now to measure the actual required buffer size, we use an automatic tool, which while the experiment is running, changes the buffer size and monitors the bottleneck link utilization. The minimum buffer size that achieves 99% utilization is marked on the graph. The experiment is repeated for different numbers of flows, from 1 to 200. As we can see here, with 50 flows or more, the required buffer size is measured at about 20 packets. This is well matched to what our analysis had predicted. that high-speed routers can buffer a handful of packets instead of millions of packets, and yet result in high throughput if their traffic is not overly bursty. For more information about our buffer sizing results and to learn how you can use our tools to repeat similar experiments, please see our website.